Start recording. And there we go. So we are going to look kind of formally here at differentiability. And get my pen going here. A function is differentiable at x equals a if the derivative of the function at x equals a exists. So again, that's basically saying if the derivative exists. I just misspelled exists at x equals a. So now remember what a derivative is, right? A derivative is a slope. So that's the same thing as saying that the slope at x equal a has to exist. Now, let's go back to our first principles of how we found the slope of a curve. We found the slope of a curve by going, the slope is the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, so that has to exist when x is a. All right, and for our example here, let's show that this function is not differentiable at x equals 0. So what is that function, first of all? Well, it is this v thing, right? It goes through 1, 1, it goes through negative 1, 1, and then 2, 2. You get the idea. Basically, it's linear in two directions with reciprocal slopes. So we notice that the slope is going to be positive 1 this way and negative 1 that way. So let's see if we can kind of figure out what is the slope at x equals 0, which again is the part that we call the cusp. This sudden change in direction. All right, we'll break for O Canada here.
O Canada and the treaty acknowledgement.
There we go. We're live again. Okay, so what is the slope at the cusp part of the graph, which is, you know, this cusp thing is right there. What is the slope there? Okay, so let's actually figure it out using first principles. So f primed at 0 would be the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h, which is the limit as h approaches 0. Okay, so f of 0 plus h is the absolute value of 0 plus h minus f of 0, which is just 0, all over h. So that simplifies down to the limit as h approaches 0 of the absolute value of h over h. All right, what are we going to do with that? Well, remember that a limit only exists if it's the same limit as you approach it from the left or from the right. So I'm going to do that. I'm going to split this up and say, okay, so what does this thing look like if it's the limit as h approaches 0 from the left? Okay, so, oops, hang on. That was supposed to look like an h. Okay, so what will that look like? Think about it. Well, h divided by h is just 1. But if you plug in a negative value to the bottom, because I am approaching 0 from the left, so I'm approaching it with a negative value, the bottom's going to be negative, and the top is going to lose that negative. So this is actually going to equal negative 1. Whereas if I approach this from the right, think about how that's going to look. The top is positive because it has to be. That's what absolute value does. And now the bottom's positive because no matter how small the number I put in for h is, it's always going to be positive. And a positive divided by a positive is a positive. So those two limits don't agree. So I'm going to say, so f primed of 0, which is, of course, again, the limit as h approaches 0 of h over h, does not exist. So I can say, I'll just kind of continue up here. I'll say, therefore, f of x equals the absolute value of h is not differentiable at x equals 0. And if we were to graph that, we would get some backup on that claim. Take a look at what happens. There's f of x, right? There's the absolute value graph. And here's what it looks like when you take the derivative of it. Let me get the original one out of the way. Let me kind of show you as I trace along what that looks like. Right? The slope on this side is always -1, which is what the graph's showing me here. This is always a -1. And when I get to 0, it tells me, it tells me it's undefined. And the same thing's true over here. The slope on the right-hand side has to be +1. And as you can see, as I get closer and closer to 0, eventually I get to the same conclusion, undefined. So let's sketch that on our notes there. If I wanted to sketch f primed of x, I would have a open dot there. So this is f primed of x, and an open dot here. Somebody asked me the other day, how come Desmos doesn't actually let you graph those open dots at the end? You have to kind of drag your cursor over to see them. And apparently I actually went to a conference with the programmer, one of the head programmers of Desmos, and they said that this is what the teachers on their committee want. They didn't want it to be that easy for students to be able to just glance at a function and tell when something doesn't exist. So it's like, is it really that much harder to drag the cursor over and check? But apparently that's what they wanted. So anyway, there you go. That's kind of a nice, now much more formal than the way I did it last time when I just kind of showed you really quick, proof that f of x is not differentiable at a point like this, a point called a cusp. And the way I kind of explained it last time is still a valid explanation. Notice that you can't draw a unique tangent at this point, right? There's a tangent, there's a tangent, there's a tangent. There's infinite tangent lines that will only touch a sharp cusp type point at exactly one place. So it's not like a curve where there is actually only exactly one point where a tangent will touch a curve. When it changes direction sharply like that, when it's a point, or again, the word we tend to use in math is a cusp, you can't find a derivative because there's no unique slope, because there's no unique tangent. So now let's move on to example 2, and this is the kind of question you had on your first quiz. So if you're looking at your test that I just gave you back, and you're wondering, why did I lose marks on number 1? Well, it's probably because you didn't do it the way I'm going to do this one. To prove something's continuous, 3 things have to agree with each other. The left limit, the right limit, and f of whatever value you're trying to find the limit at, or the slope at. So the first thing I'll do is I'll say, okay, so what is g of 1? And now, I had some people who, when they were doing a question like this, they plugged 1 into both of those things, but actually, you're kind of not showing me that you understand. The x is 1 actually only belongs to one of these equations. Which one? Notice, yeah, the bottom one. Notice that this means that it belongs to that one. So people who showed me f of 1 in all 3 of the equations we gave, or 2 of the equations we gave, you're not showing me that you understand that actually 1 belongs to the bottom one. So that's the only one I have to find. So 1 minus 1 squared is equal to 0. So I'm expecting 0. So now let's find the limits. So let's find the limit as x approaches 1. Let's do the left first. Okay, so of g of x. I'll just write it that way. So okay, so g of x, if I'm approaching 1 from the left, which function am I in? Well, when x is less than 1, it's this function. So I want the limit as x is approaching 1 me write that better. As x is approaching 1 from the left of x minus 1. And I can just plug that in. That's going to be 1 minus 1, which is 0. And then the limits as x approaches 1 from the right of g of x. Okay, if I'm bigger than 1, I am, according to this equation here, I am this function again. So the limit is going to be, as x approaches 1 from the right, is going to be 1 minus 1 squared, which is, oops, sorry, hang on, I meant to put an x here. Then I'll plug in the 1. There we go. And these three things agree with each other. So now I can make the conclusion, therefore, g of x, hang on, g of x is continuous at x equals 1. Which means that if I draw it on a graph, I don't have to lift my pen. So let's actually draw the graph. X minus 1 has a y-intercept of -1, and it has a slope of 1. And then, of course, it's up to 1, but not including. So it goes up to here, and then it's an open circle, right? So there it is. But the next function is x minus 1 squared, which has a vertex at 1. So that makes it a solid dot again, and a parabola like this. Now, I didn't draw that very good. But, in fact, I drew it so badly that I want to try it again. Let's see. And then, there we go. I like that a little better. So now, it is continuous. Now, does that mean it is differentiable? Well, again, if it's differentiable, the slope has to exist. So let's see if we can find out if the slope exists. Okay, so it's differentiable if g primed of x, which would be the limit as h approaches 0 of g of x plus h minus g of x all over h, this must exist. So does the slope exist at this point here when x, oops, at this point here when x is equal to 1? Well, let's see. Let's try from the left first. G primed of x is equal to the limit as h approaches 0 of, that'd be x is 1, so 1 plus h. Oh, hang on. I forgot the other part of the function. It's x minus 1, right? So minus 1 minus 0 over h, right? I'm just using this function here because this is the one from the left. So there we go. So that's x, and I replaced x with x plus h. And that is going to be the limit as h approaches 0 of h over h, because the 1's cancel, minusing 0 doesn't change anything. So we get a slope of 1, which we kind of knew. We could kind of tell just by looking at it that this thing here has a slope of 1. All right, let's try it from the right now. G primed of x is going to be the limit as h approaches 0. Okay, the right function now, remember, is this guy. Right, so I'm going to use that one now. So I want the limit as h approaches 0 of g of x plus h, and x is 1, minus g of x, and again x is 1. But g of x this time is the function x minus 1 squared. So that's going to equal the limit as h approaches 0. So plug in 1 plus h into x minus 1 squared, and I'm going to get x minus 1 squared. G of 1 is still 0. And what's that going to turn out to be? It's going to be the limit as h approaches 0 of, and as you can see, this one's going to turn out differently. The 1's still cancel, but this is now going to be h squared over h. What's going to happen as that approaches 0? Well, that's going to be the limit as h approaches 0 of h, which is 0. These two slopes don't agree with each other. So this, and again, just to show you this, of course, this is the slope at x equals 1 as we approach from the left. And this is the slope at x equals 0 as we approach from the right. From the right, forgot the word the. So they don't agree with each other. So that means that the slope at x equals 1 doesn't actually exist, because the slope as I approach it from one side isn't the same as the slope as I approach it from the other. So graphically, what will this look like? Well, as I approach x equals 1 from the left, I have the continuous slope of positive 1. As I approach from the right, I have the linear slope of h, or of x, I guess I should say. Right? Because remember, the derivative of an x squared is an x. And Desmos will back that up. You can graph. I have shown you in the past how to graph piecewise functions. If you ever need a refresher on that, just come and see me. But basically, here's the piecewise function right there. And as you can see, that's a much better cusp than I drew. And you can really look at that and say, oh yeah, that's a point. There's no way I could get a tangent that's unique at that corner, because there's infinite lines that would exactly just hit the corner. None of them are unique, so there's no unique slope there. And when I actually ask it to graph the slope, graph the derivative, I get what I expect. I get a broken line here. So this thing has a slope that exists at 1, and then it jumps down to 0, and then has a slope of, I guess that'd be a slope of 2, right? That'd be a slope of 2x. Okay, so there we go. That's basically the more formal version of the differentiability lesson. I'll stop my recording.